Hello, I'm Shivani Rajput. Welcome to this video on programming with Qiskit. In the last video, we were using the circuit composer where we were dragging and dropping the gates, the operators in order to draw the circuit. And we saw the code automatically generated in code's editor view. But here we have to code in order to draw circuit. So let's get started. So this is the view of that quantum lab composer. So yeah, I'll start with the entanglement experiment. So first, let me rename this notebook. I'll rename it. Let's create a quantum circuit with two qubits and two classical resistors. As we remember from circuit composer video, the first thing to do is to set our qubit 0 into superposition. And how do we set into superposition? So let me first create quantum circuit. Here it shows it is two classical and two quantum and two classical bits. It. Now what we have to do, we have to do the superposition. For superposition, we need to use the not gate, Hadamard gate, sorry. So after that, the we applied it on qubit 0. So now next step was to apply the C naught gate, and C naught gate can be applied as because I have mentioned the source and the target. So the source is 0 and the 0 qubit, and the target is the qubit 1. So now we want to measure it. So we want to put them into measurement. We want to measure it on classical resistor. We'll have to give the mapping of which qubit map to which classical resistor. So we will map each qubit to the respective classical bits. So this is the kind of circuit which we want to see. So that's exactly the circuit that we have created using the circuit composer. So we have applied Hadamard on qubit 0 here. We have applied Hadamard, and which sets into the superposition that we have entangled qubit 0 and qubit 1. Then we drag and drop the measurement. Now next step is to set run and run on composer. So let's see how we can circuit composer. So let's see how we can do that here. So first to do is we call for a backend, and so we are calling a air to get the backend, and I'm going to mention the simulator as well. So I'll be using the Quasm simulator in our circuit composer code. So we are going to use the Quasm simulator here as a backend server requested for a backend air. Then I'll declare a few variables. So let's get started coding this. Here execute is the function. Okay, it will show error. Okay, I'll need to declare execute in the very beginning. Wait, backend. And now this is the number of shots we had to give. So by default in the circuit composer we saw that it was 1024. So I'll be using the same value and storing the result in dot result. And then next I'll call the count result dot get count, and I'm going to use the name count function here. We'll get the counts or the probabilities, and we have to pass the quantum circuit. So let's print count. Run this particular. Okay, yeah, it will show error. Oh, needs to be underscore execute. Yeah, let's add this execute here and run this particular cell. Okay, now when I'll run this, it won't show any error. So yeah, here we can see that exact, not exact, 50% probability of having the qubit, both the qubit in 00 or in the 11. So let's try to see it as a histogram. So in order to do that, first we have to import library, that is qiskit.tools.visualization. So wait, from plot histogram. Okay, what happened? We okay, spelling visualization. So yeah, we have called this, and it has imported the library. So let's draw the histogram. Okay, here we see that it is close to 50-50% chances. So chances of having both the qubit being in state 0 or both the qubit being in the state 1. So okay, now we saw these result in circuit composer as well. So this is how we actually run it in simulator. So let's see how we run it in actual hardware. So provider, let me code it simultaneously and explain you. First we need to load our IBM account. Okay, it will load our IBM account. So yeah, it's loaded. Then we have to call the provider. So yeah, provider gets us the actual hardware. One thing is the we here we are using provider, and for the simulator we were using the air. So provider gets us the actual hardware and the air gets us the simulator. So this is the difference. First of all, let's see different kinds of provider available. So for that we need to call this provider dot backends, and it will show you all the providers and simulators available, the backend. So here we have the IBM Q simulator in the, that is the Quasar simulator in the very beginning. So we have the Quasar simulator, and we have different backends. We have also we can see here the IBM Q lemma and all this. So I'll just directly go ahead and do this particular code. So yeah, let me call the further commands. So yeah, provider I can use IBM Q Bellum. So let me paste it here. Okay, let's run this. Yeah. Now I'll store the result and here backend is simulator, and let's just store the result in this dot result function. Count. I can copy the same code from the upper cell, this thing, count, and result dot get count. We paste it. Okay, so yeah, you can see jobs sent to IBM Q Vellum as we have called it here. And here we can see that around 48% probability of getting both the qubit in state 0 and around 41% of probability of getting both the qubit in state 1. So the rest two we are seeing is not the stage of perfect entanglement, and that's account for the gate errors. So now in the qubit itself, so this is the way to write the code and run it in actual circuit. And yeah, we can see the count here also, that probability of having both the qubit in the state 0 is this, and both the qubit in the state 1 is this, and these are because of error, noise error, or gate error in the qubits. So yeah, let's move to the next experiment. So I want to differentiate between block sphere and Q sphere through the next experiment. So first, let me hit a new file. I can hit new file, or else I can use this thing. So it will create a new file here, and let me rename this. Okay, okay, invalid name. Wait, I can call it visualization simply. Visualization. Okay. So yeah, it has created the visualization. So you can see some auto-generated import cells created here. So we can rename the file. We have renamed it. So what we really want to see is difference between the Q sphere and the block sphere. So first we need to import the Q sphere and the block sphere plotting function from visualization. So let's me create import that from Qiskit. Import plot state, oh sorry, state q q sphere. What happened? Qiskit dot, okay, spelling mistake. Visualization dot q sphere, and next is from Qiskit dot tools dot visualization import plot block. Notice the spelling of block here, okay? It is BLOCH. Block. Multi. So this has imported. So after importing this, we need to create a simple quantum circuit. Okay, this time let's restrict ourselves to create a quantum circuit of one qubit only, and then we'll slowly process if we need more. So first let me create it. So now, now we are going to get the state vector simulator backend. So now let's call simulator and say state vector simulator. So let me call that state vector underscore simulator. Yeah, you can check spelling because by typing fast we usually do spelling mistakes and that then it will show error. So yeah. Now let's call this simulator and then this is the state vector simulator and we ask it from air backend and then ask it to give us the state vector simulator. So let's do it. Yeah, dot get backend and I'll be using the Quasm simulator. Next, I have requested the state vector simulator and I can just directly run the circuit. So next we need to execute the circuit which we call the QC. I have initiated it with QC, the quantum circuit on state vector simulator, and then we'll store the result. So for that, result execute QC backend is simulator, comma. We can decide. We can store it the result function, and then let's so yeah, so let's call the state vector result so as a variable and then the result and we pass the circuit so as we want to get the state vector result. So okay, then we will plot it. So let me create a variable that is a state vector result. Okay, so it will execute the result dot get state vector and we pass the circuit. Okay, so let's try to plot it. So let me call the plot block multi-vector vector and we'll pass the result here in order to get the perfect visualization. Okay, execute. Yeah, again we have to import it here. Execute. Executed. Oh, I did a blender here. I have used the Quasm. Instead of it, I have to use the state vector as we need to uh, use the state vector for this particular experiment, not the Quasm simulator. So, state vector simulator. Now it won't show any error. Let's run it. Yeah, that is what we want. So here it is. It is start from it starts from the center of the sphere and lies on the equator and it points straight up to the north pole which is the zero state. Now let's try to display the state vector result in the q sphere. So all we need to do is just to pass the state vector result and let's run it. So wait. So here we can see that the difference. So this is the Q sphere, and sorry, this is the Q sphere, and this includes the phase information where we can see here, and the state vector representation by the color coded title, and here it is blue because here it is blue because this is the phase angle of 0 radian. Now let's do some changes in this particular circuit, and let's try to flip the state of the qubit from 0 to 1, and we'll be using the NOT gate to flip the state. Let's flip the state. So for that we need to pass circuit dot x, and we did it, and then let's call the result and execute it. So I'll be copying the same code from here. So yeah, we can see that it has flipped to from cat 0 state to cat 1 state. And now let's place the qubit to the superposition using the Haramat gate. For that, I'll be passing it to, and then calling the same. So it is in the superposition state, and this is in the block sphere representation. Let's represent this in Q sphere. So simply we need to call plot state Q sphere, and you will see the difference of the visualization here, and I'll pass this state vector result here as well. Okay, so yeah, here you see the difference. In this, it was showing only it was showing only one arrow here, which shows the qubit in the superposition state. But here it is not showing that these are the two qubits we have used. It's just a representation, because when we applied superposition on the qubit, that particular qubit, it will show different amplitude. Like when in cat 0 state it was showing different, and it in cat 1 state it is showing different. It just because of different amplitude, it doesn't mean that it has two qubit. We have two qubit here. It's just a one qubit, and it is showing the superposition state because of different amplitude. So yeah, we can see blue color here 0 degree radian, and that yellow color here, that is pi 180 degree. So it flipped to it did a counterclockwise rotation, so 180 degree, which means that it's in superposition state. So now let's move to the next experiment, that is teleportation. So let me import the new file, and new Qiskit notebook, sorry, and rename it to the teleportation. In classical computer, it's very easy for copying anything. We used to copy our files within laptop, phone, computer. But in quantum computation, it is not possible to have exact copy of an unknown quantum state. So this is what is the no cloning theorem. So what does it exactly mean? What does it exactly mean? It means that it is not possible to create an identical copy of unknown quantum state, but there are ways to do it. Okay, we can say that there are ways to do a quantum communication. So there is a way by using an entangled qubit and few classical registers, and we can actually teleport the information from one qubit to other. So here we are not actually transferring qubit from one location to other. We are just teleporting the information which is was previously being held by one qubit to another qubit, and we are doing it by with the help of additional qubit, which is used for creating entangled pair, and couple of classical bits that are having the measurement result. And once this info is teleported from one place to other place and one qubit to other, the first qubit no more has the information, so that's what's the quantum teleportation is. So now let's try it just step by step. Let's see it step by step. So these are the auto-generated cells and the imported library from Qiskit itself. So let me add matplotlib for in order to draw the circuit in a better way. So histogram to see the result. Now start creating a circuit. So I'll be using 3 qubits, quantum bits, and 3 classical bits. So let's now, and over here we'll do some kind of operation. So first of all, I'm going to apply NOT gate to qubit 0 in order to flip the state. So yeah, I have applied it. Then what I'll do, because I'm going to transfer that is state 1 into the state of qubit that particular qubit 0 into the q2 state, in the qubit 2 state. So I'm going to add barrier over here just to make the circuit look better. So qc dot barrier. After that, I'm going to add Hadamard on the qubit of Bob. So after that, a NOT gate to qubit 1 and 2 in order to entangle them together. For NOT, we'll be using and again barrier for the clear circuit visualization. So and let's draw the circuit to see how it looks. Yeah, NOT gate on qubit 0 and Hadamard gate on the qubit of Bob, and then we have entangled the qubit 1 and 2. This is the ancilla qubit, this is the qubit of Alice, and this is the qubit of Bob, and they are doing the operation here. So let's move ahead. And the next step we would be we have to add a CNOT gate between the qubit 0 and 1 in order to entangle them. Let's apply it. Okay. Then Hadamard gate to qubit 0. Then we will entangle them. Okay, wait. Let me add a barrier here, over here for clear visualization. And again, let's draw the circuit. Run this particular cell. So yeah, we did it. Now, yeah, we can draw it. So now once Alice actually applies this, she goes and measure the qubits. So, and depending on the situation, Bob can do adjustment. So I'm going to measure qubit 0 and 1 and put those in classical bits of 0 and 1. So let's do it. This is the classical quantum bits, and this is the classical. And wait, 0 and 1. So now we are going to add the C naught gate to one the qubit 1 or 2 in order to entangle them, and then we will be using the control Z gate to put the qubit 0 and 2 together. So yeah, uh, this is the results. So we are starting with the qubit 0, and then we are flipping the state of ket 1, state of qubit 0 to ket 1, and it should have kept 1, or it should have 1 at the end. So when we measure qubit 2, we measure at the end, so it should have the value of qubit 0, that is the kept 1 at the end. So let me get the simulator to see the results. So first, yeah, okay, we can decide the number of shots as well. That is yeah, again it will when we will execute it, it will show error, because the execute, we have to first import the execute function here. So in the very beginning we can import the execute function over here. Now if I'll run this, it won't show any error. So next is then we can call plot histogram. This time I'm not going to call count separately and then pass it in the plot histogram. I'll use it directly. We can use it directly. We can do that by result.get count. So yeah, here is the result. So we are only interested in the qubit 2 state, and which is always 1. We can see here this is 0 1 2. So this is 1 1 1 1. No matter about the state of qubit 0 or qubit 1, whether it is in 1 or 0, we only have to focus on the qubit 2 state, and which is very good, which is in one state only. So it means we are successful in this particular experiment. So we have actually transferred the information from qubit 0 to qubit 1, because as we know, initially it was qubit 0, then we applied NOT gate and it flipped to its state to 1. Then we have imported the information from qubit with qubit 0 to qubit 2, and after applying NOT gate it was in 1, and we have seen here ultimately the state of qubit 2 is in 1 only. So yeah, that is what teleportation is all about. We only transfer information. So There are a few cute key things to remember. Okay, so the Qiskit is using Jupyter Notebook, as we know we are using it here, and it's in Pythonic interface, and you can run the cell at a time, and you can also download the entire code. And here we can see the documentation. There over here the Qiskit documentation, the notebooks, the textbook, and the IBM quantum services, all the things available here. So for the self learning, and the tutorials over here. So we can make use of it in order to understand Qiskit more clearly. So yeah, in the next video we'll be started discussing about the algorithms. So that is it. Thank you.